So, as I mentioned in the introduction, I'm at the Joint Genome Institute, which is part of the Lawrence Berkeley National Laboratory. I'm specifically in the plant genomics group, and we take the fresh genomes that come off of our sequencers and that have already gone through assembly, and if it's a brand new reference genome, typically someone in our group, sometimes including me even, will then put that through our automated annotation pipeline. But ultimately, we need a way to disseminate that data to the users who want to make use of that. And that was the primary motivation behind the website Phytozome.net. And since then, we've for quite a number of years now. I believe the first version came out in something like 2008. We also, every new major release, adding new genomes, pulling in some high-quality reference genomes from external folks like TARE and the folks behind the rice genome to sort of fill out areas in the phylogenetic tree. I'm sort of already going through my Phytozome introduction, so let me flip right to there. So here's Phytozome version 9, which is the current version that's live. And so at this point, this is 42 genomes, I believe. And aside from just serving the data to the public, we also build custom gene families at various internal nodes of interest phylogenetically. And so it's actually much more of a comparative genomics investigation site for folks who might want to do that. And we have been in the process for most of this year in not only adding additional species, building towards a release of Phytozome 10, which will be 45 genomes incorporated in our gene families and clustered and so forth. And sort of going through a perfect storm of updating the UI completely with the tool replacement. We're still trying to figure out, so we currently use Biomart for structured querying of all of these different elements. And I believe we're going to keep that around, but we're also building in Intermine because we're starting to get buried under expression data and SNP variation data and so forth, and we needed a more robust way of serving that data out to the public as well. So I think those are going to coexist. And then what I'm going to focus most of my time today on is discussion of moving from GBrowse to JBrowse and what that is entailed with this many genomes. So just as a quick overview, since we're still very much finishing up development, this is kind of a screenshot of our dev server, so some of our facts are a little vague right now, but this is sort of we've kind of hit the number of genomes where, even though the tree structure interface is pretty useful, it kind of has diminishing usage with the number of genomes involved. So we're moving to a more query-based thing, and this pane as well will scroll back and forth, and so you can pick your organism of interest by image as well. And just to quickly show, so this would be a specific gene view in the new interface. It's a very similar structure to the current Phytozome, where we have very tab-delimited breakup of the information that's displayed. As part of our annotations, we go through a whole suite, pretty much running everything in Interpro, and then converting those to Panther and PFAM domains and such. And we have a little graphical representation here, some PFAM domains. And then so with the new interface, we're going to be able to display variation data and SNPs in context of the particular gene and the surrounding regions. But the other big one is the gene family view. So here's a particular cluster that perhaps doesn't have the greatest name, but is one of the gene families that we built at the Browse node. And from here you have a full list of the members of that cluster and a breakdown of the different domain topologies of each member, and to see which, so this one maybe is perhaps not as robust a member since it's missing the green and the blue domain and such. But really, what it comes down to is the genome browser itself. So here I'm going to switch gears almost entirely and start talking about the back-end architecture and getting everything together. Those of you who've built GBrowse databases in the past are workflow for this. In prior versions of Phytozome is we gather GFF3 for pretty much every track, and that goes into a seek feature store database and a MySQL server, and that's then read directly by GBrowse. So we have this idea now where we need to instead be converting this data for use in JBrowse. And the main problem is that when you start dealing with 45 genomes and an average at least 8 data tracks that are GFF, that's an awful lot of data to convert. So sort of, at the low end for some of the simpler annotation data for the chlorophytes, it's only 5 or 6, but for example, Chlamydomonas, which has a lot of additional support tracks, and as well as alignments of prior annotations, since that community is very particular about being able to search for ancestral gene names. That has 27 tracks. And as well, we're starting to deal with a much larger variation in the feature density. Your typical transcript tracks are just tens of thousands, but since we're a sequencing facility, we produce a lot of RNA-seq data, and we have our own pipeline now that will take the short Illumina reads and assemble them into longer, full-length transcript, EST transcript type data that then feeds into our annotation. But that still leaves us with needing to display those alignments. So you're starting to deal with tracks upwards of 4 million, probably. I think these are just 2 examples from our 45, but I think as things go on and as more data keeps going, and every year we sort of, the number gets larger and larger. And so that itself presents a bit of a challenge. Luckily we have, since we're part of the Berkeley lab, we have access to the NERSC Supercomputer Center, and we in particular have a compute cluster of about 550 individual nodes and 4,600 cores. So I started thinking, okay, well, how can I leverage this for the data conversion process rather than just sitting there and waiting for 45 genomes to sequentially build, even though, in theory, right away I can parallelize for all 45, but I still need to wait for, if I just run the software as it comes out of the box from a JBrowse download, I would essentially be waiting until I've converted all 4 million EST sequences before moving on to the next support track, and they may be the same size or even larger. So to sort of think about that graphically a little bit, here, of course, the reference sequence preparation is nice and fast and really nothing to worry about. And then depending on whether you are converting from an existing Perl database or directly from flat file GFF3, the JSON data generation process kind of expects that you're going to each track in series before moving on to indexing for keyword searching and being able to display something. And just to highlight that these are sort of points in the data conversion process where, at least when I started working with this process, with this software, the process was very serial in nature. So I took a slightly different approach, and this is kind of very naive parallelization, in large part because the conversion by either flat file to JSON or BioDB to JSON expects to be able to write to the track configuration file as it is processing data, which is why you need to process each track individually. So how about if I just create a different output directory for each track, maintaining all of this with bash scripts and such. And then I can parallelize the conversion of each track for each genome all at once, and potentially fire off a script that sends a couple hundred jobs to the cluster, and it can process all 45 of my genome tracks, all 45 of my genomes and all of their individual tracks all at once. Of course, then there's error checking since you're dealing with cluster nodes and such, and then consolidating back into the original output directory to then feed into indexing. And that actually, for being a pretty simple approach, worked really well. I had done some initial testing looking at BioDB to JSON. So we certainly have existing feature store databases for Phytozome 9. And just to reorient ourselves again here, these are the parent feature counts only for the different tracks for poplar tree. Again, with a huge amount of ESTs aligned, but also a fair number of blast alignments that we include as annotation support. And so if I were to process this data in full in series on the cluster, and really the metric here that is the most important is wall clock time. That's the effective amount of time you're waiting for your software to run. That took about 6 hours. Once I parallelized that, there's the two in particular, sort of at either extreme, the alignment of a prior annotation in transcripts ran in 2 minutes, and that largest track of EST alignments ran in 3 hours, so effectively cutting the processing time in half. So for most people, this is not a huge concern because you're probably downloading JBrowse, setting up your data, and running with it. But our release cycle is such that even if a particular annotation has not updated, the support tracks for things like blast alignments and so forth always change to reflect updates to the annotations that are being aligned. So that was the primary motivation. Turns out that from that, being able to move to just running from flat files, of course, is much faster than dealing with MySQL connections and the overhead of talking to a database. And so this, again, looking at, in this case, the two highest, instead of 3 hours, these now run in less than 10 minutes. And so that was really nice. Sort of removing that particular time bottleneck from the process. Yeah, and then just looking at the numbers versus 6 hours, it's effectively a 12-fold reduction in the amount of processing time And this is just to get your JSON together to move on. So now we come to the subject of name indexing, and I would say that that's still a major time bottleneck, largely due to the nature of that particular data structure. But we have worked with Rob really extensively, and he's produced a number of wonderful little improvements, in particular the algorithm itself, since 1.10.7, which was somewhere September, August, something like that, is dramatically sped up. Attempting to just run this on the popular genome prior to those changes, it seemed like it would maybe finish before the heat death of the universe, but effectively would not finish. So there are a number of little improvements that are sort of maybe or maybe not be well documented, since only people who are dealing with crazy amounts of data like me really need to worry about it. Since this is still a serial process, we now have the idea of incremental indexing, so you're not just sending an entire genome worth of data to the indexer. You can index each track in turn, and that's really nice because the support tracks that do change from release to release are really only a certain few classes of them. So if we're not necessarily expecting an annotation to update every year, we can have built everything to this point, index everything but that, and then take a tarball snapshot of that index at that point, and for the next release, it's that much simpler. We just update the JSON track data for the tracks that changed, that we knew were going to most likely change, and then incrementally add an index for that as well. Also, we were very interested in having a variable amount of auto-completion for the JBrowse search engine. Auto-completion, at least in our hands, is quite powerful and useful for things like transcript names. A little bit less useful for EST names and the names of proteins that are aligned. And as well, since it's the EST and the BLAST tracks that are by far the largest amounts of data, to build auto-completion for absolutely everything would just mushroom the size of the index to quite a large extent. So we turn off auto-completion for pretty much all of the support tracks and just run it for transcript tracks, and that's working out really well for us. As well, we also include custom search attributes, which I think is something that's only been available for a few weeks now. And this is only mostly useful for us because from the front end, it's nice to be able to have a unique link that's built on our internal database IDs for a particular transcript, because we are not guaranteed that a transcript name is unique. An example would be taking an existing annotation where there's a new assembly, but it's a project that's far enough along where we're not going to dramatically change the structure of the transcript names. And really, ultimately, what we're going to do is build new gene models and then try to map existing names over. Well, then having the alignment of the old annotation as an additional track would mean that searching by transcript name would almost always come up with multiple search hits. And so just for being able to link directly from our front end into the region of the browser and display what we want, it's good to have a unique link that's available. And so we have this sort of additional GFF attribute that is also indexed, and that so far is working pretty well as well. So I'm going to spend the last little bit of time here talking about two types of data that are slowly taking over my life. So the Joint Genome Institute, has traditionally been a sequencing facility for reference genomes. And that era is kind of coming to an end, and especially now with the capabilities of RNA-seq and all of the various applications of that, as well as Illumina reads in general for sequencing across a whole population and comparing that to the reference. We needed some pretty robust ways of dealing with that. So I'm going to run through a couple of case studies of data dealing with diversity and variation data, and then also some look at expression. So yes, diversity, definitely one of our fastest growing data types. Using the poplar tree again as an example, there was a study published in 2012 by some collaborators of ours, doing an initial pilot investigation of 16 different individuals, sort of sequencing, selected from all along this range here in the western part of North America where poplar grows. These were resequenced with Illumina and aligned to the reference, and SNP and indel variant data was produced. And that's all fine for 16, but when we reanalyzed this with the GATK suite, even with really stringent filtering, that gave us 6.7 million SNPs in poplar. Plants in particular have really much higher level of variation than metazoans. And I did mention this as a pilot study. This has been slowly expanding to over 1,000 individuals. And so we have this data up in GBrowse now. However, the way that the only way I was really able to do that at the time was to take the VCF from GATK and convert that into GFF3 and put it in Seq Feature Store. And so right away there, we're talking 7-8 million features. So that's a nice long involved process of its own. And if we ever wanted to update any of the metadata, you pretty much have to reload an entire database. But now with JBrowse, this is so much easier. So here's a snapshot of the poplar genome in JBrowse as it is now. Here we have a big wig of RNA-seq coverage that went into this genome annotation that were assembled into these sequences that produce these transcripts. And down here we have the current state of displaying variation data in JBrowse, where it's reading from the VCF directly, which is really wonderful in my mind. And we do a little bit of color variation here, depending on the annotation of the effect of the SNP or indel on the sequence, especially if it's within an exon. So red, which is maybe a little hard to see here, is indicating a frame shift. And I do look forward to being able to use an allele tower type of display for this as well. But this is certainly working pretty well for us right now. And I think Rob did not mention that one other thing that he's been wasting his time helping me with is an ability to write configurations in more of a GBrowse format where it's plain text, where I can have line breaks, because we do fairly extensive reading and formatting of the metadata. So if you click on one of those SNPs, this is that high impact SNP, causing the gain of the stop codon. Our BCF data gets annotated using SNPF, which reads through and compares to the transcripts themselves and gives you a sense of whether this particular SNP is downstream of a gene or not. And really the more important information is when it's within a transcript and has some potential effect. So the design here is a little bit more in a prototype stage than I'd like it right now. It's a little 1995, but just a matter of applying some CSS, I believe. So a lot of the information on the genotypes and depth and reads per allele and things like that are available from the main JBrowse interface. Here I'm making my own custom pop-up mostly to be able to parse out and display the SNPF variant data in a more meaningful fashion. And then to tie that back into the new UI, here's that variation track that I had mentioned, where this is essentially reading the same information that it came from the VCF file, and placing it in context of the genome structure at this point. And then our intention is for all of this data to eventually be something that can be queried on the fly from this interface and also be downloaded through Interpreter. And so not to spend too much time here, although it looks like I have a couple more minutes. One of the other, so this comes out of having way too much RNA-seq data to work with. So for the JGI, we have this initiative starting up called the Gene Atlas, which is basically, Jeremy Smuts called it modern code for plants, which is probably pretty similar in intention. So we have a core set of our genomes where we are specifically gathering transcriptome data pretty much for however many different ways you can grow it. You can grow a plant, how many different, every single tissue we can possibly get, and just building that up into a huge resource with some other candidate biofuel stocks being added in there too. And so the RNA-seq reads are then aligned and analyzed with CuffGIF to give us some FPKM values which indicate the expression level difference in that particular tissue or whatnot. So the example here, where there's this data already and in JBrowse, for me to demo a little bit here is in Phaseolus, which is the common bean. More interesting genomes where the black bean and the kidney bean are essentially the same species, just different cultivars. So we take that CuffGIF data and convert that to GFF3, and we can do some color variation. Everything I've built for JBrowse here actually is taking advantage of the canvas tracks universally, so that's been great. So we have some color variation from light blue to black, depending on the relative size of the coefficient of variation of your FPKM values. So for this genome level, for this gene locus level expression here, a nice pop-up will come up and give you a sense of the values, and here's all of your different tissues, and they're pretty similar. So that gets a much lighter color, then say this black transcript track, where what we're seeing is genetic expression levels in flower and not really anywhere else. And the eventual goal, again here as well, it's great that it's in the browser and can be searched and scrolled through and looked at, but the intention is for this to be something that can be queried through our main web interface as well. So there's some quick summary. Flat file conversion is certainly pleasantly fast, and it's a little uncertain to me whether the framework of scripts and whatnot for parsing out those jobs to an SGE engine is something that would be something others would want to use, but it's certainly something I could contribute back to the project. And just for example, again, we had to update the BLAST and GlideX tracks for pretty much everything when we finally finalized the soybean genome, which is aligned to pretty much everywhere across the way. So I reconverted all 45 genomes for the primary alternate transcript track, BLAST and GlideX, in parallel, and that ran in 2 hours. Yes.
Can you say what you're converting from or to?
Yeah, so it's GFF3, the features. For transcripts, it's the full mRNA, CDS, UTR, parent-child relationships, things like our alignment tracks, our match and match part, sort of simple HSP displays. But since these are so much more feature-rich, they're pretty large amounts of data to process there. And it's all getting converted to JSON format for the NC list access by JBrowse.
Yeah, I didn't go over what the NC list format is, but is the beyond this format that JBrowse uses for statically representing feature data in a way that can be queried efficiently using static HTTP requests.
Yeah. So name indexing is certainly much better. The major problems I seem to be having now are disk I/O on the cluster. But that's a problem everyone faces dealing with the compute cluster. So runtimes, for whatever reason, are really wildly varied, depending on. I think that a lot of it has to do with which node I get assigned to and what other jobs are running on that node, and idiosyncrasies like that aren't too important. The fact of the matter is that I can index an entire genome now in under 3 hours if I'm lucky. And then for things like RNA-seq and SNP data, it's nearly drag and drop as far as displaying it in JBrowse now, which is really nice. So as far as acknowledgements go, at the JGI, Dan Roxar is the head of the eukaryotic program at the JGI, and also works pretty closely with us plant folk. David Goodstein is my boss, who is the manager of Phytozome itself. I spent a lot of time talking about the popular genome, which is annotated by Xingcheng Xu. The GATK analysis was done by Jeremy Phillips, and CUFDIF and expression analysis by Ming Zhang. Of course, none of this is really possible at all without Rob back there. Something I'm certainly very grateful for. And in general, we pretty much are using all of these components here on a daily basis these days. In order to, we had a very flat, non-denormalized database structure for a lot of our annotation work, but now that we're dealing with SNPs and multiple members of the population and not just the reference, that was not really feasible going forward. So we've moved that in general into Chado, and then treating our old structure as sort of a materialized view of Chado for a given genome, and serving the website from that. And everything here is funded by the U.S. Department of Energy, Office of Science, which I may have forgotten to mention at the beginning. The reason the Department of Energy is interested in plants is biofuel development and the development of cellulosic biofuel feedstocks and things like that.
All right, thank you.
Any questions?
Any other quick questions? I kind of like to get in the, all right, go ahead.
What's the projected release date for Phytozome 10?
So we are a little behind. A lot of that has to do with the integration of some of these new things into the updated front end. Our original intention was to have it released for PAG, but such. And I also want a pony. Yeah. Since we're making such a huge update to everything, we're going to be maintaining Phytozome 9 as available as well, since we don't want to frighten our user base away. I believe we are projected somewhere in a 2-week range or so for the new front end and things like JBrowse.
Okay, maybe we can move along so we can have Dan come on up. He's going to talk about badges. I like badges.